The definite integral, we call it the definite integral because the answer is a definite number. We come up with a definite answer. Here is what we call the fundamental theorem of calculus, and it is something we touched on yesterday. It's simply this. If you differentiate that primitive function, you come back up with function x. That's all it's really saying. It's the backwards to differentiation. Some properties of our definite integral. Well, we know this one. When we're integrating a polynomial, we add 1 to the power over the power. Something I didn't necessarily stress yesterday, notation. You'll notice the limits have moved to the right-hand side of the problem rather than on the left-hand side, so we tend to do that, and we use square brackets. I have seen people use a straight line with the limits on, but this tends to, I think, be the more common way of doing it. Constants. You see, an integral symbol is a grouping symbol. So just like in algebra, you can factorise, but the difference is you can only factorise constants. Because if you pull an x out, well, that's what you're trying to integrate. So you don't want to take it out of the integral. So only constants can you pull out when you're factorising. That's the one that simply says we can do it piece by piece. We don't have to do it all in one hit. Here's an interesting one. If I wanted to integrate from a to b, and in between a and b there's this some other number c, if I wanted to, I could theoretically integrate from a to c, then integrate from c to b and add the two together. I should get the same answer. That is useful for some problems, which we'll get to later. Now, the answer will always be positive if our function is always positive. So we see the picture, if what we're integrating is always above the x-axis, I should end up with a positive number. Whereas if the function is actually below the x-axis, I should get a negative number. And if you're looking at two different curves, if one curve is always below the other, then their results should also be like that. If function x is always below gx, then the integral should give you a smaller number. And if you think about it, if we're talking about areas, that makes sense because, of course, the higher one would have a bigger area. You are allowed to change the limits. I said we always start with the one on the left and go to the right. You don't have to. But if you want to swap them, what's going to happen is you'll get the negative of what you want because instead of going a minus b, you're going b minus a. So if you want to swap them, you can, but change it to a negative out the front. So you make sure you get the right result. If you've got an odd function, symmetry about the origin, that integral will always turn out to be 0. And that's all to do with, because the area below is negative, so the area below will cancel with the area above. You add them together, you get 0. Whereas if it's an even function, what you could do is just integrate from 0 to a and double that answer because you know the symmetry on the left-hand side, it should be exactly the same. Why do we do that? Well, because 0 often is an easy number to substitute in. So if you notice it's an even function, could save you some time. And if you're looking at compound functions where you've got things multiplied together, remember, odd function times an odd function is an even function. Odd times an even is odd, even times even is even. In other words, if they're the same type of function, when you multiply them together, you'll get an even function. If they're different types of functions, multiply them together, you get an odd function. Let's look at some examples. So here's 6x squared. I mean, you don't have to factorise, but you could if you wanted to. I could say, oh, let's pull the 6 out, integrate the x squared, add 1 to the power over the power, we get a third of x cubed. Sub in the 2, sub in the 1, there's our answer. I mean, you could just as easily leave the 6 in there and go 6 divided by 3 is 2 and do that. Cube root, well, we're going to have to turn it into index form first. So it's x to the power of a third. Be careful. Add 1, we get 4 thirds. Turn it upside down, because remember we're saying it's 1 over. So in effect, you're turning the fraction upside down. So it's 3/4 x to the 4 thirds. Now personally, certainly for ones like this, I put it back into third form because I'm dealing with irrational numbers here. Your calculator's going to come up with a decimal approximation. It's not going to give you the cube root of 5. So if I go back here, when I sub in, I'm okay, because I know that's going to be 5 times the cube root of 5 minus 0. I get the exact answer, not an approximation. So that ends up being 15 times the cube root of 5 over 4. Trig, we've only dealt with polynomials so far. until you realise the sine function is an odd function. Notice the limits, you've got symmetry about the origin there. It's going from -2 to 2. So sine to the power of 5, we're going odd times odd times odd times odd times odd. Okay, odd times odd is even times odd is odd times odd is even times odd is odd. We've ended up with an odd function. And so I know the answer is 0. Here's one, but if I look at each individual term, I've got a mixture of odd and even functions. Look at the symmetry. It's going from -1 to 1. I could, rather than integrating all these terms, rewrite it like that. I know all of those odd functions, x cubed and x, they're going to give me an answer of 0. I don't need them there. Get rid of them. That leaves me with 2 even functions, 2x squared plus 1. Now, because it's an even function, I can use the fact that it's symmetric and go twice from 0 to 1. 0, in this case, a very easy number to substitute in, and we get our answer. They're all little tricks. You don't have to do them. I mean, you could integrate each term separately if you wanted to. You're going to get the right answer, but they're just little things. If you notice them, you can save some time. Sketching the signed area function, or the primitive function. So this is what's called the area function. Going from a to x of some function comes up with the area under the curve. Okay, we will get function x minus function a, whatever the primitive function happens to be. Here's a graph of our function. We now want to graph the signed area function. How do we do it? Okay, to make life easy, I'm going to tell you what all those areas are equal to, and to make it real easy, I'm going to make them all equal to a. So every piece here is going to be a. Okay, so I've got 4 a's there. Okay, above it, I will now draw the signed area function. So a, that x-intercept, I'm going to plot it. Area A must be equal to 0 because have a look at the formula. It'll be function A minus function A, which of course is 0. So I know I can plot that point. It's an x-intercept. What that therefore means, this curve I'm about to draw is going to be a stationary point because its derivative, remember the second one down is the derivative graph, the derivative at A is equal to 0, and we know stationary points happen when the derivative is equal to 0. Now, what about the 0? What happens there? What's its value going to be? So we're now saying, what's the integral from A to 0? Well, looking at my picture, I know the integral from 0 to A. I'll swap the limits, but I've got to put a negative sign out the front. Therefore, it must be negative A. So I'll plot negative A. Okay, let's work out B. Area B turns out to be negative A. Why? Because it's function B minus function A. What is function B? Function B would be going from A to B, which is A, but it's underneath. So it's negative A. So that's from A to B, and that's what we want, isn't it? Because our formula says, what is it going from A to B? So I can plot that. This one, therefore, means that B will actually be a possible point of inflection. You really got to think through this one. Because the second derivative, if we were to draw it, would be the first derivative of this one. Now, look at B. I have a stationary point on the derivative graph. So the second derivative, it would be 0. Second derivative means possible inflection point. Let's have a look at C. We're going from A to C. We will end up with negative 2A. So going from A to C, we've got 2 below, which is minus 2A. Plot that. Right. Also means C is a stationary point, because look, on the derivative graph, it's equal to 0. Area D will end up being negative A, because if we go from A to D, we've got minus 2A below, we've got A above, put them together, you get negative A. Look at those dots, we're starting to see what the curve's looking like. Notes, in the interval from C to infinity, our derivative is continually increasing, because it's getting more and more positive. Therefore, our graph is increasing because our derivative is always positive, and we said that defined an increasing function. There is the area function. All right, there we go.